We're excited that you're here. For those who are going to be asking questions with our setup today, we will invite you to unmute. So we have to click something first, then you'll accept it to be able to ask your question. All right, and as people have questions that they're hoping to ask, should we have enough time, you can add those to the chat box and we'll see about integrating those if we have enough time at the end. Okay. All right, thanks everyone for being here, and Dr. Roberts, it's over to you.
Thank you. Welcome to each of you. What a special day this is for the Gatton Academy. We are very happy to have all of the students from the Academy as well as the staff. We want to welcome WKU faculty who've joined us and alumni of Gatton who are especially interested in space. We are glad each of you is here. What a special day this is. This morning, the Gatton Academy received the National Consortium of Specialized STEM Schools Innovative Partnership Award. And awards are so nice. It was exciting. And that, of course, was for our partnership with Costa Rica and Cloudbridge, where research is done most Januaries. Any January we can travel. It is also a wonderful day because we have the opportunity to communicate and talk with Dr. James Green, Chief Scientist at NASA. But I want to begin by introducing our Gatton Academy students to Dr. Green. They are high school juniors and seniors taking a full schedule of WKU classes. They will graduate from high school with a minimum of 60 college hours that they have taken at Western Kentucky University. They number 184, and they represent all parts of the Commonwealth of Kentucky. The honor of having Dr. Green with us today is due to our friendship with Lieutenant Colonel Terry Wilcott, a WKU graduate with a major in math, who went to Frankfurt with me way back when we were lobbying to create an academy for the state of Kentucky. So Terry has been a good friend over a long period of time. Terry is NASA's Chief of Safety and Mission Assurance and an astronaut who commanded 2 shuttle missions. Terry introduced us to Dr. Green, and today it is our honor to have Dr. Green with us. This may be the shortest introduction I have ever made, but when I've been thinking about what to say about Dr. Green, other than that he is NASA's chief scientist, I was pretty stumped. So I think being the chief scientist of NASA is the introduction for you, Dr. Green. Welcome.
Perfect. Well, thanks so very much. It's just a delight to be here. I'm going to start off giving a quick little overview of some of the fantastic things that NASA is doing and what we're up to. So I'm going to share my screen, and let me bring up a few charts that we can go over. So let's talk about how we explore space with science. And it turns out NASA has 3 basic themes, science themes that they go after. The first one is protect and improve life here on Earth. The next one is search for life elsewhere, okay, beyond Earth. And then discover the secrets of the universe. In these 3 themes, we do an enormous number of research activities and build spacecraft and visit places all over our solar system and beyond. Now, we do that as organized sets of science teams. In fact, here are the teams. There are 5 of them. One is an Earth science team. Another one is a planetary science team. Another one is an astrophysics science team, then heliophysics, and then biological and physical sciences. Now, these teams, of course, concentrate in certain areas. Earth science, well, we want to look at the Earth. We want to protect the Earth. We want to measure how things are changing on the Earth over time. Planetary scientists go all over the place. And in fact, they have completed, with our flyby of Pluto, our initial assessment of our solar system. And now we're delving into more details. The astrophysics group, they look beyond the solar system. So they look at other stars and nebula and galaxies and black holes and the center of galaxies and all kinds of things in the cosmos. The heliophysicists study the sun and what the sun does to our solar system. In fact, the sun, which is this enormous ball of gas, what it does is constantly outgasses, and it can be very active sometimes. And so the heliophysicists are real important in terms of how we would travel in space, and we do and perform experiments in space. And our major activity is our biological and physical science group, which concentrates on, right now, living and working on space station. And so let me mention that in your entire life, there has been somebody living and working in space on space station. This year, we've had 20 consecutive years of humans in space. And now we're planning to go beyond. We're planning that next big step to enter a new realm of exploration by going to the moon and then onto Mars. And we also, in these 5 groups, have a whole array of missions. Now, I'm not going to go through all the spacecraft. In fact, it's almost impossible to do that. But we're going to pick out a few things to talk about. There are more than 100 active spacecraft that NASA has up and flying today, and many tens of experiments on space station that are performing all kinds of biological and physical science experiments. And so we'll just pick a few things that we do in space. Well, let's talk about each of our themes. What about protecting and improving life on Earth? What does NASA do in that? I thought NASA was just about going out into space. Well, we observe the Earth from space by looking down. And what's really important is we do that from various vantage points. One is indeed the International Space Station. Now, although at any one time we'll have anywhere from 3 to 6, and in fact, this next month, we may have as many as 7 astronauts on space station with an upcoming flight of taking 4 up. We also use space station and have experiments that are hanging off a variety of these appenditures on space station, and they all look down, except for a couple that actually look up because they are also astrophysics missions. So what do some of these instruments do? Well, over a period of time, and it's a matter actually of a few days, we can get a global overview of several different types of measurements. So NASA has a lot of satellites that look at the weather. So some people might say, why is NASA launching weather satellites? We can get that information off the Weather Channel. Well, where do you think the Weather Channel gets its data? Okay, it gets it from NASA. And so we provide a lot of measurements about the weather because we're studying the atmosphere. We want to know about the Earth's surface and its interior. We want to measure changes in our atmosphere and how that varies over time. And it's not just about the seasons. We want to look at the carbon cycle and in our ecosystem. You know, plants love carbon dioxide, and how are they growing, and what's happening in that balance of generating oxygen and generating CO2. Atmospheric composition is really important. In fact, there's layers in our atmosphere that without them, life as we know it would not exist, such as the ozone layer, which is a molecule of 3 oxygen atoms that really love ultraviolet light. And if it didn't, if that layer of ozone wasn't there, that light would make it to the surface, causing skin cancer and killing crops, and it'd be a very different world than we know today. And then, of course, there's a lot of biological material in the ocean. The basic food chain is the phytoplankton that live in the ocean, and they're very temperature dependent. So we want to study the water. Now, of course, NASA, when it looks and you see hurricanes and disasters and things going on in the world, these are measurements that are coming from NASA satellites. Now, NASA doesn't predict the path of some of these. There's many different organizations that do that, but we can gauge the amount of clouds and therefore amount of rain that's available, and then cause major damage, and really be able to assess and be part of the assessments that allow us to be able to move the population and protect human life and property. So indeed, NASA does an enormous amount of earth science work, and that's not really known very much. Now, one of the things that NASA is known for, of course, is the search for life beyond Earth. That is a grand question. Even the ancient Greeks wondered as they looked at objects in the sky moving back and forth that didn't follow how the stars moved, calling them planets, whether there were life on those planets or not. Well, we now have a major activity going on where we have searched the solar system looking for life. And right now we haven't found life beyond Earth, okay? All the planets have gone through 4.5 billion years of evolution, and some may have had life in their past, like Mars. Now here is a Mercator projection of Mars, okay? This is the surface of Mars, and here are the location of landers and rovers that have been on the surface of Mars operating for some time, and many of them have come and gone. You see the Vikings, 2 Vikings, Spirit and Opportunity, Pathfinder, Phoenix, those were all NASA missions that were launched in the 90s and the 2000s. And of course, the two major systems on the surface of Mars that are working today is the InSight lander and the Curiosity rover. And on the way to Mars right now is the Perseverance rover, and Taiwan, which is a Chinese lander and rover. And so these are the locations that they're going to be at. Now, how to read this map is the whites and the reds are the highlands, and the blues and the purples are the low areas. And so as you see, many of NASA's missions are actually in the green and yellow area. And it turns out we now know that Mars had an enormous amount of water on its surface. And so it would be in these lowlands, in that northern hemisphere of Mars, where most of the water would be. Now, here is an image on the surface of Mars by the Curiosity satellite. And we call them satellites sometimes, but this is really a rover that's now on the surface, roving around. And on the end of it, it has a drill that goes into the surface. It drills a hole about the size of a dime, okay, and goes down about 1 inch and pulverizes the rock. And that material then comes up in these small finds, these small debris. Now, when we first did this, this actually is our first 2 holes on the surface of Mars. And you can see the red patina on Mars. It's all oxidized on the surface. And when we drilled down, we were shocked because this isn't red. This is gray Mars. Mars in the past had gray soils. And in fact, what's in those soils are all the key ingredients for life. There's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The soils are moist and they have nitrates, which we can use as fertilizer. So if you saw the movie The Martian, the question would be, well, can we grow crops in the Mars soil? And it turns out here, the soils are alkaline. So what would work really well in these soils are more like asparagus and beans, okay? Now we're assuming there'll be places on Mars, other places where the soils would be more acidic, where the potatoes would grow. So yes, Mark Watney indeed could, as supplementing the nitrates with additional fertilizer, grow crops on Mars. We're pretty certain of that, all right? So that's pretty exciting. But I have to tell you, if I had to eat 2 or 3 years of asparagus, I think I'd just take my helmet off and walk outside and be over with it. But, you know, potatoes, I could probably. So what's really exciting about all these landed missions and orbiters at Mars is we've been able to understand the history of the planet. And here's what we see. Mars, like the Earth, is 4.6 billion years old. And when it came into being by accreting material, it also accreted an enormous amount of water, which flowed on its surface. And by 3 billion years, Mars lost its water. Now, we think what happened is it first lost its magnetic field, which the Earth still has. And then the solar wind, where the sun constantly outgasses, stripping the atmosphere away, eventually evaporated the oceans on Mars, and then the solar wind stripped it away. So we need to, when we go to Mars, look at that rock record, because the rock record is the history of not only the evolution of the planet itself, but also of its climate and its oceans. We think it went through climate change very rapidly, perhaps within 100 million years, lost most of its water. And that rock record is what we really want to have to be able to determine what happened. Well, this is our next mission. This is the Perseverance Rover. It looks much like Curiosity. In fact, we've taken all the experiments out of the Curiosity model, and we've put in new instruments and created this new rover called Perseverance. And it has many instruments from different countries. But what's critical about this rover is that it's going to core rock. It's literally got a drill that will go in and spiral around and core rock, producing a piece of sample that looks like a piece of chalk. Now, you kids may not know what chalk is, okay? But this is like the large Crayola crayons, okay? So in my day and age, we had white chalk on blackboard, but indeed, same kind of size. And we're going to put these in metal tubes, and we lay them down on the ground, and we're going to be able to core more than 40 different locations on the surface of Mars. Now, this is really exciting because we're going to go get them and bring them back. And that's what this next mission is all about. It will leave the Earth, cruise to Mars. That's on the left side of this diagram. Land. And what will land is a rover plus, it's called a fetch rover, plus a rocket, a Mars ascent vehicle, all right? And that rover will go and pick up the samples in these tubes, bring them over to the rocket, stow them in the rocket. We'll erect the rocket from Earth. We'll send the commands, and we'll blast that rocket off and put the samples in space. So it'll be a little capsule with those samples. And then we'll have a spacecraft capture them and bring them back to Earth. And with the rock record in our hands, in our laboratories, We then can read the pages of history that are in these geological records of what happened on Mars. So this is really important. But what's really interesting is the mineralogy of the rocks, how the atoms connect and organize into a lattice that forms the minerals themselves, and what those connections are all about tell us all kinds of things. For instance, on Earth, there are over 5,000 minerals, but 300 of them can only be made by life that grows, lives, and dies and becomes part of the rock record, all right? So the samples are really going to tell us whether Mars also had life in its past. Now, in the few minutes I have left, we want to discover some of the secrets of the universe, right? That is another major theme that NASA does. And what we do is let's talk about one of the most spectacular objects that's in our backyard, and that's the moon, okay? Now, the moon goes through one day in a month, and here we see that 1 month of observations. And as you look down on the South Pole, you see these craters, but some of these craters remain in the dark. They are permanently shadowed over the entire time the moon is in its orbit around the Earth. So what's in those permanently shadowed areas? So here we see that south pole of the moon, and we see these permanently shadowed craters. And what we've done is we've colored that with another set of data that we've taken from orbit that indicate that the moon has water trapped in these permanently shadowed regions. But it's not just water. We think the moon had an atmosphere early on as it was developing. We actually know that it had a magnetic field. It also lost its field, and the solar wind stripped its atmosphere, which is what's happening on Mars. So that's happened on the moon 4 billion years ago. But what's on the moon then is in these permanently shadowed areas are these lunar atmosphere volatiles like water and carbon monoxide, carbon dioxide, but also because the moon was so close to the Earth early on when it was made, we also expect some Earth atmosphere. So this is a spectacular place to go. In our plan is called Artemis, and our plan is to have many different robotic missions going to the moon, many of which will go to the South Pole, interrogate this area. And then we'll have a capsule. The first one is Artemis 1. This will fly from a large rocket that we're also building called the Space Launch System. It's actually being built out of Huntsville, Alabama at the Marshall Space Flight Center. And what will happen then is that capsule will be uncrewed, will go around the moon and come back. And that's our shakedown mission. Okay, we'll test everything, make sure everything's working. And we expect to launch that late next year. Then our Artemis 2 mission will do the same route, go out, go around the moon and come back, but it will have astronauts. Then we'll build a space station, it's called the Gateway, that orbits the moon. And then Artemis 3 will dock with the Gateway. The astronauts will move into a descent vehicle, which will go down to the surface, where the first woman and the next man will walk on the surface of the moon since the Apollos. And we want to do that by 2024, okay? We're only a few years away. And then they will go back up to the Gateway and come back in the capsule. Now, our plan is that we're going to have many more Artemis throughout 2020s. And we'll be interrogating the moon, learning to live and work on a planetary surface before we then go to Mars. And so we want to explore the moon further. Well, we plan to live on the moon for many weeks, perhaps several months. So we're going to try to live off the land by going in these permanently shadowed regions and getting water. And we can drink the water. We can also break the water apart because it's made of hydrogen and oxygen. We can breathe the oxygen. We can break that water apart in hydrogen and oxygen and create rocket fuel, because we need hydrogen and oxygen for rocket fuel. And so there's many different things that we're planning to use and leverage the moon for. And then starting in the 2030s, we will begin a process of going to Mars. And so this is just a little taste of some of the things that NASA's doing and the science that we're uncovering. So what I'd like to do now is turn it over to you and answer any questions you may have. And I hope you enjoyed this little taste of what NASA's up to. Thank you very much.
Great. Oops. Great. Thank you, Dr. Green.
My pleasure.
That was a great overview.
My pleasure.
So I think Jacob Harris has our first question. So I'm going to invite Jacob to unmute. All right.
Hello.
Yes, Jacob.
Hi. I was wondering, like, what your typical day is like at NASA.
Okay. Okay. Even though I've been home, although I'd go into work occasionally to pick up a few things, but I've been working from home since March. My day is pretty much the same in the sense that early on in the day, I'll review some of the new scientific discoveries that are going on. As chief scientist, my job also is to make sure that NASA science is proceeding. I work with a whole team of scientists at many of the NASA centers. Then we'll go through a series of meetings. My job also is to advise the administrator, the head of NASA on the scientific activities. Also, we talk about the health of some of our spacecraft and some of the new things they're finding out. And then if I have a little time, I do a little scientific research on my own. So that's been pretty much my day, whether it's been in a building or electronically. But what's really happened, of course, is during the time we're all sheltering in place, we've had to use a lot more of the electronic tools, like Zoom and WebEx and Teams and just a whole series of different types of software. And NASA's been doing that actually for several years. So it really was pretty easy to transition from meeting on a regular basis into a new mode of working. Although in many ways it can be harder.
Okay. Thank you.
Sure.
Okay, great. All right, now I'm going to invite Keegan Congleton to unmute and ask his question.
Hello, my question is, what projects is NASA currently working on that involve climate change?
Oh, okay. So as you see, a significant chunk of what NASA's doing is observing the Earth. Right now we have about 20 satellites that are observing Earth, looking at Earth, okay? And looking at all sorts of things, from the amount of carbon dioxide that's emitted, where it's emitted, how it moves, to looking at ozone, seeing how the ozone is protected, how it changes over time, another really important atmospheric constituent. So these measurements are then put in an overview of all changes that are occurring. And then we talk at a variety of conferences and we turn that information over to the administration, no matter if it's a Republican administration or a Democratic administration. NASA's been involved in making these observations. And then we model what will happen also. Many of the big climate change modelers are actually planetary scientists. You know, we studied Venus, which is incredibly hot. You know, it's hot enough to melt lead on the surface. And it's because it has a runaway greenhouse effect. So we did that in the 70s and early 80s, and we took those computer codes to Earth in the late 80s and into the 90s, and that's when we discovered the importance of these greenhouse gases and how they change the climate here on Earth. All these trace gases are important to measure. So I'm a planetary scientist, and I can tell you that the climate has done nothing but change. So the Earth is 4.6 billion years old, and the climate has changed all over the place, okay? So in this day and age, it's not about the fact that climate is changing, is the rate of change, okay? For instance, 12,000 years ago, the Northern Hemisphere had a glacier that extended in the United States through New York and over the mid and part of the upper part of the United States. And when it retreated, it carved out the Great Lakes. And that was about 12,000 years ago. And so that's an element of how the climate changes cyclically over time.
Great. Thank you very much. Okay, Sophie is up next with her question.
So you touched on this briefly, but how does NASA decide what exactly to explore? There's so much to explore. So what process do you use to determine if a mission is a good use of resources at that time?
What we do is we go to a place called the National Science Academy, okay? So this academy was actually put in place by President Lincoln in 1862 during the Civil War, because he wanted the National Science Academy or National Academy of Science to give him recommendations. And so it is an independent group of the top scientists in the United States. And so we asked them in each of the areas, in planetary science, earth science, heliophysics, and biological and physical science, what is the top questions we want to answer? You know, NASA, NASA can do really good science, but we don't want to do really good science. We want to do the best science. We want to do the top science. We want to answer the most important questions. Those are the things that we want to go after. And so the National Academy helps formulate those strategic plans. And that's where we get our themes. Those themes actually come from our interaction with the National Academy of Sciences.
Great. All right. Ashwin is up next.
Hello. I was wondering if you could elaborate on NASA's engineering design philosophy and how NASA approaches engineering, how it approaches the safety of their crewed spacecraft from an engineering standpoint. Thank you.
You bet. So NASA builds missions, and unfortunately, it's when we go to Mercury with a spacecraft, it's not like going to Pluto, because Pluto is very cold. The sun is hardly shining there. And at Mercury, it's incredibly hot because we're so close. Those produce enormous engineering challenges, all right? So once we define what we want to do, where we want to go, the measurements we want to make, then begins the engineering that will create the spacecraft that will enable us to go there. So we start, of course, with what we've done in the past, what works in the past. We want to see if it, then model it to determine if it's going to work in the new environment. We bring in new elements. Sometimes new technologies are perfected that we then bring in, and that helps us. Things that might be lighter, things that might have a huge change in thermal capacity. I'll give you an example. There is a nanoscale silica arrangement of material called aerogel. And this is a very light, very airy, it's got plenty of spaces with material that's just connected in almost one atom strings of atoms that are connected through. And it's a tremendous insulator. It's really light. And we wrap all our batteries around them when we're on the surface of Mars, because Mars can get to be 80 below zero. You know, that's kind of almost, you know, at night, the normal temperature. So indeed, we need to insulate our batteries. So those are the kind of things that we have to consider: the thermal aspects, the variations, the amount of light that we receive, and the power that we need. Now, Curiosity, another piece of it that's engineered in a particular way, is because we want it operating during the day and during the night, we need to take a power supply with it that doesn't rely on the sun. And so we use nuclear power. And that nuclear power then charges a battery and runs all our experiments. So it's just like plugging in your iPhone all day long and having it work. And that's what we do with our rovers on Mars. Like Curiosity and now Perseverance. So engineering is a really big part of what we do. And one of the spectacular things that NASA does is create these environments that allow us to go to places, you know, create these fabulous spacecraft, and they're all very different. Each and every one of them are different, and there's all good reasons for that.
Okay, thanks. Okay, Star is next.
Hello? Yeah.
Yes.
I had a question about SpaceX and Starlink in particular. I've heard a great deal of concern about the Starlink satellites being especially bright and then thus obstructing like observations like of space at twilight. Is this is this as big of a concern as it's being depicted as? And if it is there anything that's being done about it?
Good question, because we are concerned. Now, the groups that are concerned are actually astronomers, okay? Astronomers that use telescopes on the ground. We have to see through our atmosphere and out into space. And as these objects reflect sunlight, they indeed can inhibit our seeing ability. So right now there's a lot of discussions going on, but the sign of the time is, I think, that we're going to continue to move towards more spacecraft, more smaller spacecraft that are in space, that will be commercial, you know, uses, from internet to taking images of the Earth and doing a variety of things for a variety of different industries, looking for fish in the ocean by following the phytoplankton, and, you know, looking at all kinds of things and that's going to continue. So as new technologies like that come on, you know, we are going to continue on with the discussion of what we have to do to also preserve the science that we're doing. So it's an important discussion, and it's not completed yet.
Thank you. All these complications with, you know, everyone's so interested in space and the commercialization of opportunities.
Well, one of the things that we're looking at is building observatories on the moon, in particular on the far side of the moon, okay, where the interference from Earth is negligible, because one side of the moon, you know, faces the Earth, as we talked about. It's tidally locked, okay? So we only see one face, so it spins on its axis in a month, and in that month it goes around the Earth, and that's why we only see one side. But that far side goes through night and day, but the Earth is hidden, and it may be one of the best places to have a variety of observatories. So with new technologies also comes new thinking and new approaches that are being discussed, and we throw all that into the mix, as we say.
All right. Annabelle is next.
Okay.
All right, so during the Artemis program, what will like the earlier trips to the surface of the moon be like? Like will astronauts spend most of their time on the space station, just kind of like pop down to the moon briefly, or will they spend a lot of time on the moon? And do you think that that setup is just going to be like altered a bit to suit Mars better later?
Good questions. So our first set of astronauts down on the surface will probably, well, our plan is we'll spend more time on the surface than in the gateway, in that small space station. But it'll also be split. You know, we'll also have crews, you know, maybe one person, maybe two at the most, in the gateway, and they may not go down to the surface at all. Okay, so but our plan is to really get down to the surface and learn to live and work there for days. Now, in the Apollos, Apollo 17 stayed on the surface of the moon the longest, and that was about 3 days. Okay, we're talking about staying down on the surface for weeks, maybe several months. And so you know, we're planning those trips out right now. But I have to tell you, I witnessed. I was in high school. Okay, I was in the same level that you are today in your education when we landed on the moon for the first time. Okay, and it was incredibly exciting. You know, even watching it on a black and white TV, it was riveting. Okay, what you're going to experience coming up will be spectacular. You know, we'll have high definition TV. It will be very different than the Apollo in many ways. For instance, when the Apollo astronauts set foot on the moon, the sun was largely overhead. In the South Pole, the sun's going to be at the horizon, and there'll be long, eerie shadows. So it'll look very different than the Apollo mission of astronauts walking on the moon, and very exciting.
All right. We have another follow-up question about the moon. So I'm going to invite Ryan Gott, one of our alumni, to ask his question.
All right, thank you. So I was wondering, what do you see as the key scientific obstacles for the upcoming moon missions?
Okay, so the things that we're working on right now that we haven't completely worked out is the ascent and descent vehicles, okay? And then the larger habitat that we would plan to put down on the moon so that we could live and work in that particular area. So those plans are coming together right now. You know, we're considering 3 different types of ascent and descent vehicle, and we will soon pick one and then build it. So right now, that's one of those things that we call being on the critical path. Okay, whenever we talk a little bit about engineering, one engineering technique is as you build things is you figure out what the critical path is. In other words, what are those things that are in your way that absolutely have to be built and ready to go before you can take to the next step. And therefore you identify those and get on them and make sure they're not delayed, because it delays everything thereafter. And so the ascent and descent vehicles are on the critical path.
Great, thanks.
Yeah, sure.
And we're really excited for Ryan, who will be joining NASA in January. So, and thanks for spending time with us today, Ryan. All right, and our next question is from Will Johnson, also an alum with working at NASA. He has a moon question as well.
Hi, do the lunar science goals of the agency change with the recent Sofia discovery of water on the sunlit surface of the moon?
Okay, so no, they actually reaffirmed what we already believed. All right, now why is that important? Well, when we look in these permanently shadowed regions and we detect material there, And that material could be one of two things. It could be water, H2O, or hydroxyl, OH, okay? So we can't really split the difference. Now you don't want to drink hydroxyl, okay, but hydroxyl has the hydrogen and oxygen, so you can tease it apart and create the rocket fuel, and you can breathe the oxygen, and all that's good. So that was always our plan, to be able to use that as a resource. But the Sofia observations, which clearly demonstrate that even on the surface of the moon, and therefore what would be in the permanently shadowed regions, is H2O. That was really great. That now really means that when we do an estimate of the amount of material that's in these permanently shadowed craters, which right now we believe is between several 100 million tons of water, okay, or it could have been hydroxyl, but we now believe now it's water. That's why the Sofia observations were really important. Man, we were just delighted. It's the material we were hoping for, and it's there.
Great, thanks. So exciting. Okay, and Annabelle has another question related to the moon that she's asking on behalf of a group of us.
What would happen if you opened a fruit like a banana on the surface of the moon or anywhere else in the vacuum of space? My guess would be they would like instantly freeze dry and that any bacteria would die pretty instantaneously. Would it then be safe to eat later if you protected it from like dust and stuff?
Wow, those sound like great experiments. You should propose them. All right. We're always looking for good experiments, but indeed, the moon's going to have, in the shadow, it's going to be real cold. All right. When we look down in these permanently shadowed regions, and we can actually measure the temperature remotely, okay, and we get a number, we can hardly believe it. And the reason why is it's so cold. It's colder than the surface of Pluto, okay? It is the coldest places in the solar system are in these permanently shadowed regions, okay? So that's really interesting. You know, talk about freeze, you know, drying anything, man, there you go. And then of course, in the daylight, you know, when the sun shines, even though the sun will be low on the horizon, and we'll get glancing views, we won't have the direct sunlight, you know, where everything will be reflecting, and the temperature is higher at the mid latitudes in the equator than in the polar region. It's still really hot, okay? And so those temperature variations are just enormous. And so all our space suits, all our habitats, all our food, observe it, how we want to do all that be taken in through experimentation. Okay.
Great, thank you. We had a whole discussion of whether bananas go to the space station, what would happen to a banana. We had a whole long conversation about bananas in space and other fruit as well. Okay, Harrison has a question, so we'll unmute Harrison next.
My question was, does NASA have any long-term plans to send probes to other star systems like Alpha Centauri?
What we're doing right now is we're actually talking about how to leave the solar system and explore the region between the stars, okay? That's kind of our first step. Our closest star, Alpha Centauri, is 4 light years away, okay? 4 light years. And the Voyagers have gotten to the point where they've just left the heliosphere, okay? Now they have enough velocity, enough momentum behind them that our sun won't pull them back. So they'll actually leave the solar system. But let me tell you how big the solar system really is, okay? When we talk about the heliosphere, we're actually talking about the extent of the magnetic field of the sun. So the sun has a magnetic field that's in this big bubble, and the winds from other stars shape that bubble. Okay? And so the Voyagers just now have punched through the bubble and are actually making measurements of the winds from other stars. Now that's really great, but in reality, they haven't completely left the gravitational influence of the sun, okay? Now that is so strong that it will be another 100,000 years before the Voyagers actually will leave the influence of our sun and go into the gravitational inputs of the other stars. So let me give you an example. The sun's gravitational influence goes out to about 50,000 astronomical units. Okay, so that's 50,000. Okay, where one astronomical unit is the distance between the sun and the Earth. Now that turns out to be about a light year. If you shined a light, it would take about a year to get to 50,000 astronomical units, okay? And Alpha Centauri is 4 light years away, all right? Where are the Voyagers? Well, the Voyagers are at about 135 astronomical units. Only 135 astronomical units. I mean, they're just really close to us when you think about the distances of space. Even though they're out in the area where they're tasting the winds from other stars. So our next big missions are to go out and really study that heliopause area, that area where we leave the influence of the sun and go and measure the influence of other stars. And so those missions are being planned now. But we won't make it to Alpha Centauri for quite a while yet.
Great, thanks. All right, Avery Linehan is next.
Hi, so I was just wondering, where did you grow up and what education did you get to this point?
Okay, so if you looked at the United States, and you take a pin and you stick it right in the middle, that's born, okay, right on Mississippi. And so the high school was fantastic. They had their own observatory. I took a class about astronomy when I was, chemistry, physics, and I took astronomy, and then I got to use the telescope, and then I built instruments on the telescope. And this is a time that, the TV show Star Trek, the original TV show Star Trek with Captain Kirk was starting to play, and the astronauts were starting to go to the moon. So it was easy for me to just get excited about space. And the instruments I were building on the telescope took images. So I learned to develop film, print film, and several things that I did was printed in a magazine called Sky and Telescope. Okay, and I was in high school. All right, so when I left high school, I went to the University of Iowa in Iowa City, and I knew exactly what I wanted to do. I wanted to be an astronomer. And so I joined the astronomy department, and I started working with one of the professors there named James Van Allen. Now, James Van Allen is our first fantastic space scientist. He built the experiment that went on Explorer 1, that launched right after Sputnik and discovered the Van Allen radiation belts. They're named after him. And so when I went to the University of Iowa, I recognized, hey, I could do astronomy from space vehicles. Okay, they were on their 54th instrument. They were building spacecraft. And so it was so easy to get involved. And so after I graduated, I stayed at the University of Iowa, got my undergraduate, my master's, and my PhD there. I got a job at Marshall Space Flight Center right away. And then from there, I went to Goddard Space Flight Center and then the NASA headquarters. So let me mention a couple things. You can do anything you put your mind to. You can prove it to yourself. I challenge you to prove it to yourself. Set a goal and make that goal, okay? Now that turns out to be really important to do, because once you're able to do that, you recognize you can then create another goal, and then another goal, and then another goal, and achieve those things. You also have to have determination. So I was good in math, and I was good in science, all right? And so it was easy for me to do a number of things, but I gotta tell you, I hated geometry, okay? Not all math is created equal, all right? And so you have to tough it out, you know? I got great grades, good grades, and some bad grades, but you know, I didn't let that deter me. You just keep going, you just keep going. And you have to have a passion for what you're doing and let that drive you to the new goal that you want to do, all right? And it's remarkable what you can achieve, absolutely remarkable, and it's only up to you.
Thanks for that. All right, Tristan has a question.
Hi, I was wondering if you ever outsource projects to outside companies, and if so, what kind of projects do you have other companies do?
Yeah, NASA actually does that a lot, has been doing that from day one. So NASA has a workforce of about 50,000, and that's at all the centers, and then contractors that work the, and then we work with another group that's probably 200 or 300,000. I think the highest total workforce was 400,000 during the Apollo era. So, for instance, when we decide on this ascent and descent stage, the designs that we're looking at are from 3 different companies. And we're going to pick the best one, and we're going to have that company build it. So it's not going to be built by NASA. It'll be built by another company, okay? So we pick and choose the things that we do based on the experience that we have. And then we bring in the companies that have experience that goes beyond what we have, and they become our partners. So that stuff happens all the time.
All right. Next up is Ruby.
Hi, I was wondering.
Go ahead.
I was wondering.
It's okay.
Sorry, my roommate also is listening. Okay, I was wondering about NASA's position or involvement in the militarization of space.
Okay, so we have zero effort in the militarization of space. NASA is your public arm. What we do is open scientific research that we do, the things that we make, the observations that we have, the data we create are placed in archives, and you can get access to those things, and you can do more research with data from the Voyagers or from missions that we've done, and we've been doing that a lot. Now, there is a little bit of a connection with the Department of Defense because sometimes they develop some things that make our job easier in terms of materials or in terms of power systems. So fundamental research that's being done in the federal government, no matter what the sector is, we want to be able to leverage and use and bring into our environment, improve it and use it. And then, of course, we develop all kinds of different technologies that they use. So it's a very symbiotic relationship.
All right. Christine is next. Christine Balance.
Okay.
There we go.
Okay, so hi, my name is Christine Belance. So it's kind of a weird, crazy question I had to ask. We're probably leaning more towards sci-fi, but I've heard before, like as you were discussing, that Mars lost their magnetic field and all this water they have, and the loss of their environment led to this climate they have. So is it possible that the natives knew like they were losing their magnetic field in their source of water, that they traveled to Earth, settled here, and through the process of natural selection and survival of the fittest, they decided that Earth was like, the most probable place to survive on. And like, we're here now. So yeah, just like the idea of, as we're doing right now, like we're discussing, our climate is changing. What should we do? Maybe it happened to.
Yes, that's a very interesting way of thinking about what's happened in our solar system over time. If we look at Venus, we now know enough about Venus to determine that it was a blue planet too. The fact that it has runaway greenhouse effect only happened about 800 million years ago. Okay, it had an enormous amount of water in it. Life could have come and gone on that planet. The same is true for Mars. Now, where life started in the solar system, clearly this planet is the only planet we know where life exists. But it doesn't mean it necessarily started here. It could have started elsewhere and was brought here. And the theory that is that thinks in that direction, that goes in that direction, is called Pampspermia. Now, Pampspermia, the idea is life, microbial life living on another planet, impacts as the planet is accreting material, blasts material up, and then that material comes and settles on another planet and begins to live and grow in a new environment. Now, what's exciting about that idea is when we go to the Antarctic, okay, during the summer down in the Antarctic, which is going on right now, I have a team of people that are in snowmobiles, and they're driving across the blinding white glaciers right now. What are they looking for? They're looking for black objects that stick out on these glaciers, and they go and they get these little objects, these rocks, and they are meteorites. Okay, they have fallen on the earth. And we bring them back, and we bring back anywhere from 600 to sometimes as many as 900 a season. And then we see where they're from. And some are from Mars, and some are from the moon, and some are from Vesta, an asteroid, and other things. So we're finding that the idea that as the Earth moves around the sun, it collects material that has been blown away from objects all over the solar system is true. Now, whether life can use that as a mechanism to travel and then come to another planet, that's the unknown. That's the unknown. We don't know that that's happened yet. Okay? But the environments on Venus and on Mars have changed so radically. Indeed, life could have started there and has now been eradicated.
So many things to think about. Okay, Lucy Rosie's is next.
I was wondering, since the rovers and the missions, they're making history, they have to have an important name. So how do the names for these missions and rovers, like how are they made? I guess who comes up with the names?
Yeah, so how do we name our rovers? So right now we have on the surface of Mars, Spirit, Opportunity, Pathfinder, Sojourner, Perseverance is on the way, and all of them were named by kids in the United States. Okay? So when we named Perseverance, Perseverance was named by I forgot his first name, Andrew, I think it is. Andrew Mather, I think is his last name. You can probably Google, where did the name Perseverance come from? And students from across the United States wrote little essays, submitted them, and we got like 80,000 of them. And we reviewed them, and then we culled them down to the top names, and then we selected one of those names. So the helicopter that we're also with Perseverance has got a helicopter, fabulous little helicopter. It's called Ingenuity, and that was also named by through another essay. And Curiosity was named by Clara Ma, and she now is at Princeton, I believe, getting her degree. So we run naming contests. So you can always apply, the next big rover we do.
That could be fun.
Yeah, it is.
All right, Leah is up next.
Hi, I was just wondering how the commercialization of space travel with companies like SpaceX, Boeing, and Blue Origin has affected how scientists and engineers do their jobs at NASA.
Okay, good question. So let me start out by saying 20 years ago, the only game in town going to space station and beyond was NASA. And in the early 2000s, we decided, hey, we've been doing this a while. There's all kinds of fantastic science on the station that's happening. And if we want to take humans beyond low Earth orbit and go to the moon, we want more commercial activities to happen on space station, okay? In a place where the gravity is virtually non-existent, okay? Zero gravity. We actually call it microgravity because there is a little gravity, but not much. And what we've been finding out is on station, all kinds of things are going on that we've uncovered. And we want more companies to come and do that. So by mid 2000, we decided we needed to invest in companies and have them build the rocket and capability to get to station. And so we picked 6 companies and invested in those companies for several years, and then down selected to 3. And after more than 10 years, those companies then got up to speed. Now we don't need to fund them anymore. And there's SpaceX and Blue Origin. And those are the companies that build rockets in their own laboratories, like NASA used to do. And we just hire them and take us to space station. And so this enables us to then save money and put that money into other things going beyond low Earth orbit. So we hope that other companies will then, instead of going to NASA to try to go to space station, all they'll start doing is going to companies like SpaceX and Blue Origin and get rides up to space station and then run a variety of experiments, do a variety of things that really can help life here on Earth in a very productive way by developing a new market. It's the space economy. And we think that it's a real game changer. Now let me give you a couple examples. And we're also partnering with different groups, different pharmaceuticals and the NIH. One of the things that we found out is that the longer our astronauts in space, when they come back to Earth and we measure their immunity system, it's like they've aged 30 or 40 years. They come back with a compromised immune system, okay? Now, we don't know how that happened, but in space, there's only one big difference: no gravity, all right? So something happens to the body where the immune system gets compromised. Well, guess what happens next? Once they're back on Earth, within a matter of a few weeks, their immune system comes back. It is repaired. Now, this is spectacular. The reason why is the elderly, 17% of the elderly die of pneumonia from a compromised immune system. We don't know how it changes, and we don't know how to repair it. But now we have, honest to goodness, examples of going into space, getting a compromised immune system where we can study how that's happening, and then how the body repairs it. We can study how that happens. And so now the National Institute of Health and many different companies are really excited about that. Because if we can crack that one, we'll save millions of lives, in the future, and extend our ability to live longer. And that's just one example.
Wow, how interesting. Okay, we have 3 questions left and then we'll close. Okay?
Mm-hmm.
Okay, so Alan Lynn is next.
Hi. What map do you use on future missions?
Alan, type your question in the chat, and then maybe Lynn could read that, and then we'd get it, because you're resonating so much I can't hear you.
This question is, what math do you and NASA use on a daily basis for your missions?
Yeah, good question. Algebra, calculus, and I mean, you name it, we use it. Geometry, okay? Even if I didn't like geometry, I've had to, grow up using it. We solve multi-dimensional differential equations, okay? Well, how we do that, though, is not necessarily with paper and pencil. We go to computers, okay? Now, every scientist in the field has certain key things that they do and do well. So what am I known for? I'm a magnetospheric physicist, okay? So that means I never met a magnetic field I didn't like. And I will look for how electromagnetic waves propagate in magnetospheres, okay? Now that sounds really odd. I mean, it sounds very unbelievable, esoteric, okay? But it's a fantastic thing to do because it enables us to look for exoplanets with magnetic fields, therefore may harbor life. So some of the early research I did could actually help find life on another planet, all right? And what I'm known for is solving multiple differential equations to be able to predict how light moves in anisotropic magnetospheres. Okay, so I don't expect you to know any of that, but other than the fact that math is just such an integral part of what we do, and that we use computers to be able to execute that math, okay? So computer science and our mathematics are intimately linked.
See, like computational problem solving. By making everyone at Gatton take computational problem solving, we're preparing you all for NASA careers.
No question about that. In fact, I learned my first language. A lot of people ask me, what languages I speak. I speak Fortran, and I speak C or C++, and that's about it. Okay, I can't speak German or Spanish or anything else. But that's just my inability to have that capability. People are so different and have different views and different capabilities, of course, and that's why they're so important that we bring in a diverse group of people within NASA. But I didn't learn Fortran until I was in college. I still use Fortran because Fortran is still the top language in supercomputers, okay? And so understanding what languages, computer languages are there, how they're used, how we implement them, and that whole trend, you know, has just been fantastic. There's just, that whole area has just exploded. And NASA's taken great advantage of that.
All right. Okay, so Will Johnson, you're up with the second to last question.
It's been 8 years. I'm having CPS flashbacks now. But Dr. Green, I was curious what your favorite mission is that you've worked on during your time at NASA.
Okay, this is I actually get this question a fair amount. So I've been on an unbelievable number of missions, and I was head of planetary science for 12 years. And you know, in that, you know, I was involved in everything from New Horizons to Pluto to Messenger at Mercury to Curiosity to Cassini. You know, you name it, I was involved in it. Okay, and so I would have, you know, when I give talks, I'd have kids come up and say, you know, what's your favorite planet? What's your favorite planet? We got to know. All right, and so it's a very similar answer, and the answer is, as head of planetary science, I love all my children equally, okay? And so indeed, I can't tell you or pick one special mission, okay? Because they're all special. They're all designed to do something different. And they've all been highly successful. And everything they've discovered has just blown my mind in terms of not even imagining what they could discover. Each and every one of them has brought new views and a new worldview to me. And so it's because of that, I can't tell you that I have a favorite. I love them all.
What a great career to have, where all the projects you do are so exciting that you're always having your mind blown with the discoveries of your projects. I mean, that's a job that we all aspire to, right? It's something that we're so excited about like that.
Yeah. So here's the secret. Don't tell anybody. I have the best job in the agency.
Hopefully all of us end up thinking we have the best job, right?
Right. Yeah.
Okay, so our last question is from Sophie.
My question is, how has COVID impacted space travel?
Ooh, good question. So, as I mentioned, we're about ready to take 4 astronauts up the station. During this time, we've actually had 2 astronauts go up the space station. And indeed, we follow all the normal guidelines. So when the astronauts train, you know, we train them in a way where we wear masks and we're separate. Our people are tested a lot. We go through a process of isolation. The astronauts are not with their families for several weeks, okay? There's no opportunity for them, after they get tested, to end up with COVID and then take it up to station, okay? So we follow rigorously all the latest science and then execute on that. Now, we keep and monitor what's happening in the environment. In fact, when this first started and we were short of ventilators, we took a part of our workforce and created ventilators. In fact, there are some new NASA ventilators that were made and produced and be able to distribute. We also got involved in some sensing tools where we could do some testing and use some of the things that we developed. Elements of that we needed, okay? In addition to the fact that we had the workforce and the ability to help the country, and we're going to do that, of course. But in our environment, we all need to work hard to stay safe and implement processes and procedures where we don't end up infecting anyone up at space station. So it's been difficult, but we've done really well.
Right. Well, when we hope everyone continues to be safe. So, well, Dr. Green, we are so honored to have you speak with us today. It's been really exciting to hear all the different aspects of what's happening at NASA, all your different projects. I also think it's been really interesting to hear about your career, you know, your career pathway and the things that people who want to end up working at NASA might need to think about for their own career path. So we really appreciate your time on this Friday afternoon to speak with us and to share your love of STEM with us, with our students, and with those of us who also love STEM. So thank you for saying yes when Terry Wilcutt connected with you, and we hope that you will join us again in person after all of this is over and we have the opportunity to learn from you again.
Well, that would be great. I thoroughly enjoyed it. I'm just delighted that Terry connected me with you, and we had the opportunity to talk about some of my favorite stuff. How can I not do that, right?
Yes, great. So students, thank you for your questions, and thank you for joining us this afternoon. All of the refreshments and the reception sort of snacks that we didn't get to have in person are in the lobby, so you are welcome to log off and go by and grab a snack. WKU faculty and Gatton alum, thank you so much for joining us and taking time. We're always excited when we can reconnect with our alumni and wish you well and connect you with our students. So thank you everyone for being here this afternoon, and I hope everyone has a great weekend.
Thanks so much, Lynette. Bye now. Take care.